Hello, this is Rick Guptill, Senior Programmer at StruSim, and this presentation was given at the National Robotic Arc Welding Conference and Exhibition in Milwaukee, Wisconsin recently. The title of this is a printer driver for welding applications. And the main idea here is for us to show you how StruSim will work like a printer driver would work. For example, here is a customer of ours that makes buildings, and so you can see that they make walls and floors and ceilings, and when they want to print out something, they have this print dialog box where they say, okay, how many copies, and this is what I want, and here, and this, and that. And the same thing can happen in StruSim, and does happen in StruSim, where they select they actually have two welding systems, one for walls and one for floors, and this happens to be the floor one, and they can just pick multiple files that they want. These are in XML format that have welds information, but they're the walls that they designed, and they print out what they want and they press go, and then StruSim starts writing out the files for the printer. But the printer in this case is this. It's a Kawasaki robot mounted on two external axes. It's got a welding controller and a welding torch, and it's got a laser, a servo robot laser to sense it. So they print those out, and they have the same thing, a stack of walls that they've printed, and the person printing those doesn't need to know anything more about welding than a person that prints paper needs to know about the internals of printing. Here's a flow chart for StruSim and what we do. We have different input files. XML you just saw. We also have IFC, structural steel, CIS2, and we could also use sort of mechanical CAD interfaces, SolidWorks, Inventor, that kind of thing like that. We classify the welds, and then we have our welding engine, and we check for collisions, and then when we're done we produce a robot welding program. In this case Kawasaki, but we could also do Fanuc or Motoman or Kuko or whatever we have. Here's an input right now that shows XML file welds. We just went over that. See, this is a brown, blue, and yellow welds. They're marked differently depending on what type of weld they are. So this is how we classify them, and we have different names for the welds that we see, so we know how to handle them. The yellow arrow means we're going to start there, and then the red is that's where we're going to proceed. So you can reverse the welds if you want to do that. We can also read welds from IFC files. Here's a structural steel member that we're going to weld this plate on the end. It has 6, 7, 8 welds with it. You can go through the welds and identify them. We can also read CIS2 files. This is a bridge section that has it's fairly large, and we'll see a video of it later, and you can see that it has a lot of welds in it that we want to classify and weld. And then here's an inventor file that we actually intersect these parts with the base part to get these welds, and so we determine the welds ourselves. So really there's several ways we can read in welds. The main idea is that we want to have seen them, and we want to have classified them, and we want to have programs. So the next time you see them, the next time StruSim sees them, it knows how to handle it. It's just like a printer, you know, you have to first tell it the fonts, and once it knows the fonts, then it can print that out. Here's the flow chart again. Now we've talked about that. We're going to talk about this part here just briefly. You want to have these weld and touch joint vectors, call them JVs. You know, it's kind of the way a robot programmer would program. You start with where you want the robot to be to either touch or to weld. And then we have these things called touch elements, which in this case is a laser, and it's measuring that seam, and you can position it. You can determine how you want your touch elements to work. You can either have one or several. And then the touch moves combine one or several touch elements. So in this case you can have 3 different laser sensors, or In some cases we use mechanical touch, electrical touch. I'll show you that also right here. So in this case, we don't have a laser mounted on this. We have electrical connection between the torch and the beam, and so we go actually in there and we can measure the side, the front, the back, the top, and we can get a position of where this plate is. Okay, so we can program that in. So even though it's pre-programmed, every beam can be a little different. We can measure the beam, and it's not a problem. Safe elements, briefly, they kind of tell us where we should move the gantry relative to the weld so that the robot can reach it with the weld JV. You can also do things like tuck the robot up to move it out. And then once you have these safe elements, you can also actually specify a rotary element on a table. We'll see that. Safe moves, kind of, you have this idea of you want to get in there and touch, and then you want to weld. So you've got pre-touch, pre-touch, post-touch. Here's where the touch happens, and then the pre-weld, pre-weld, post-weld, and post-weld. These are extreme. Normally you just need a pre-touch and a pre-weld. You just go in there, move the JV, touch, move to the weld JV, and then weld it, and then you're gone. And then you go to a safe position so that you can move to the next weld. Weld elements specify there's two ways to set it, either manual or automatic. Manual means you go in through and set the actual push angle and work angle that you want when you see that type of weld. Or an automatic actually is really useful for when it has to sort of change the push angle on the fly. It has to start with one and sort of tuck the torch in, and then move to the other side where it changes the push angle. Alright, here's an example that kind of alluded to. So here's us programming it. We select these welds, these 6 welds that we want to program. Now sometimes because of collisions you can't program the welds, and in this case we have these 3 vertical brown welds, four vertical brown welds, and they're all treated the same, and so they said, well, we don't want to try to automatically adapt. We want to actually set the push and the work angle. So we said, well, we just can't reach it because it's too close to the flange on the bottom and too close to the flange on the top. Okay, but once we've established that, we actually can keep track of the welds we can't do and keep them in a file that they can go back and touch that up. So let me see if I can get a so I'll create the Kawasaki files that then we'll send to the robot, and we'll get a real robot in here. There's the code it generates. So we'll bring in the actual, this is the actual robot running. We'll try to sync them up here. So there's, on the right is welding, on the left, when it torch turns purple, that means it's welding. The simulation's a little bit ahead here. It's catching up, okay. So it measures it with the laser, and it says okay, and then it starts welding it. So that's how this works. Here's another example. This is of the big beam, of the big bridge section. 2 robots welding, so that's all specified through the CIS2 file. Heavy welding. Here's an example where it's moving along a curved. This stiffener in here is actually curved through here, and we weld the whole thing with one pass. And then this example, we read in a IFC file and we put it in this clamp, and we have all these plates, and then we read the plates off and perform the welds. Alright, please let us know if you have a welding example you'd like to do and have any questions. Thanks.